Welcome back to Cosmos in a Pod. We're jumping right back into our space and astronomy series with episode 2.
Yeah.
And today, we are going deep on one of the biggest mysteries in astrophysics. Dark matter.
It really is incredible when you think about it.
It is.
Most of the matter in the universe is this stuff that we can't see or touch.
Yeah, it's like a cosmic riddle.
Right.
How do we even know it's out there?
Hmm.
What was the first clue that something was, off?
Well, picture this. You're watching a merry-go-round spinning super fast.
Okay.
You'd expect the horses on the outside to go flying off.
Yeah, makes sense.
But in galaxies, the stars on the outer edges are moving way faster than they should be, based on all the stuff we can see, like stars and gas.
So something must be keeping them in place,
Right.
providing this extra gravity. It's like a cosmic glue or something.
Exactly. That's where dark matter comes in. This invisible stuff with a ton of gravity. It doesn't emit or absorb light. It's like a giant invisible web holding galaxies together.
I see.
Pretty cool, huh?
Okay, so we've got these stars zipping around way too fast, and scientists are like, hold on a second, there's got to be something else out there. Who first proposed this idea of dark matter?
That was Fritz Zwicky back in the 1930s. He was studying a group of galaxies called the Coma Cluster, and he noticed they were moving way faster than they should based on their visible mass. He even called it Dunkelmaterie.
What's that?
It's German for dark matter.
Ah.
Yeah, it's pretty cool. He was ahead of his time.
But, that's kind of a wild idea from the 1930s.
Oh, absolutely.
People must have thought he was a little crazy.
Yeah, it took a while for people to come around to the idea. It wasn't until decades later, the 1970s, when Vera Rubin's work really solidified the idea.
You're a ruin, okay.
She was studying individual galaxies and found the stars on the outer edges were orbiting at the same speed as those closer to the center.
Wait, so the stars further away from the center of the galaxy are moving just as fast as those closer in?
Exactly. It
Yeah.
shouldn't be like that.
Yeah, you would think they would be moving slower because they are farther away.
If only the stuff we can see, like stars and gas, was responsible for gravity, then yeah, those outer stars should be moving slower. But they're not.
And the only way to explain that is?
Well, there has to be a lot of invisible matter,
Wow.
adding its own gravitational pull.
So Vera Rubin's observations pretty much clinched it.
Yeah, pretty much.
There's something invisible out there affecting how galaxies move.
Right.
But the big question remains,
What is it?
what is dark matter?
Yeah.
Do we know?
We don't know for sure.
Really?
That's the million-dollar question. Scientists are working hard on it.
I bet.
It's a really tough problem.
Okay, so what are some of the leading ideas?
Well, one of the top contenders is something called WIMPs.
WIMPs.
Yeah, short for weakly interacting massive particles.
Okay, I gotta ask.
What's that?
What does that even mean? Break it down for me.
Sure. Essentially, WIMPs are hypothetical particles that are thought to be heavy, but don't interact much with normal matter. So they just kind of pass right through us.
Like cosmic ghosts.
Exactly.
So they are massive, but they don't like to interact with the other particles.
Yeah, they like to keep to themselves.
And that makes them pretty hard to detect, I imagine.
You got it.
Is that why we haven't found them yet?
Pretty much, yeah.
So how are scientists looking for them?
They've built super sensitive detectors deep underground to try and catch them.
Deep underground. Why?
Well,
Is that like a mine or something?
it has to be shielded, right?
Oh, I see. Okay.
So it can't be disturbed by cosmic rays and things.
Uh-huh.
The idea is that if a WIMP passes through, it might bump into an atom and create a signal.
So they're setting a trap, hoping that a cosmic ghost will bump into it.
Kind of, yeah. And some experiments have reported some interesting hints,
Have they?
but we need more data before we can say for sure.
So we're on the edge of our seats waiting.
We are.
It would be huge if they definitively found one.
Yeah, it would be a game changer for physics.
Okay, so we've got these underground detectors trying to catch WIMPs,
Right.
but you also mentioned particle accelerators earlier.
Yes.
How do those fit into this?
It's a different approach. It's like the opposite of underground detectors.
How so?
Instead of passively waiting,
Yeah.
we are trying to create them.
You mean create WIMPs?
Uh-huh. By smashing particles together at incredibly high speeds
Whoa.
to replicate the conditions of the early universe.
So we're recreating the Big Bang in the lab
Kind of, yeah.
and hoping that some dark matter pops out.
Exactly.
That is wild.
The idea is if we recreate those super high energy conditions, we might produce dark matter as a byproduct.
I see.
It's a long shot.
What kind of particle accelerators are we talking about?
The Large Hadron Collider, the LHC.
Oh, yeah, I've heard of that one. It's the one in Switzerland, right?
Yes, It's the most powerful one in the world.
So they are smashing atoms together, hoping to make some dark matter.
That's right. And if we did create it in the LHC, we could study it in more detail.
Okay, so two approaches then. Sensitive detectors searching for WIMPs underground.
Right.
And powerful particle accelerators trying to create them by smashing things together.
Exactly.
Sounds like scientists are covering all their bases.
Yeah, we need to use every tool we have to try and crack this mystery.
All right, so let's say we do figure out what dark matter is.
Yeah.
What could we learn? You mentioned earlier it could have big implications.
Absolutely.
For physics and even lead to new technologies.
Yeah. First of all, identifying dark matter would complete our picture of the universe's fundamental building blocks. You see, our best model of particle physics, called the Standard Model, doesn't include dark matter.
Okay.
It doesn't even explain what it is or how it works. So finding dark matter would force us to change or extend the Standard Model.
It would be like rewriting the physics textbooks.
Basically, yeah. It's a huge step forward in understanding the universe.
At the most fundamental level.
At the most fundamental level.
And who knows what new mysteries we might uncover.
Exactly.
Maybe even whole new areas of research we can't even imagine yet.
It's possible.
This is incredible.
Isn't it?
So it's not just about figuring out a scientific puzzle. There could be real-world applications, too.
Definitely. Throughout history, breakthroughs in physics have often led to new technologies that change the world.
Like electricity.
Exactly. Or computers. It all started with understanding physics.
So what kind of technologies are we talking about when it comes to dark matter? What could it be used for?
It's hard to say for sure, but the possibilities are pretty amazing.
Give me some examples.
Okay, well, if we learn how to manipulate it, maybe we could use it for spacecraft propulsion or new forms of energy.
So like spaceships powered by dark matter.
It sounds like science fiction, but it's not entirely out of the question.
That's amazing. Or maybe even new ways to communicate.
Yeah, it's possible.
Wow. So revolutionizing physics, new technologies, spaceships.
Yeah.
But there's also something almost philosophical about this whole quest for dark matter, isn't there?
Oh, absolutely. It's humbling to realize we're surrounded by this vast invisible universe.
It's true.
We're only beginning to understand.
Shows how much we still don't know.
Yeah, it's like an invitation to keep exploring, to keep pushing the limits of what we know.
Absolutely.
And to never stop asking questions.
Exactly. The more we learn about the universe, the more we realize how much more there is to learn.
Right.
Okay, so we've covered a lot of ground. The evidence for dark matter, the ongoing efforts to understand it. But there's one more aspect I want to touch on before we wrap up.
What's that?
The implications of dark matter for the fate of the universe itself.
Oh, wow. Okay.
We're thinking big now.
We are. Yeah, it really is fascinating, the scale of it all.
It is.
85% of the matter in the universe. And we still have no idea what it is.
It's humbling, really.
It really is.
So we talked about gravitational lensing and simulations. Yeah. Are there other ways we are trying to pin down what dark matter is?
There are.
Okay, tell me more.
Well, one approach is to try and detect the particles directly.
Directly? You mean like catch a dark matter particle?
Yeah, kind of. It's a huge challenge, though.
I can imagine. These particles barely interact with normal matter, right?
That's right. But scientists have built some incredibly sensitive detectors, often located deep underground to try and find them.
Deep underground?
Yeah.
What?
They have to be shielded from all the background noise.
Oh, okay. Yeah. Makes sense.
Cosmic rays and other radiation could interfere with the measurements.
So you need to go deep to create a quiet environment.
Exactly.
To increase the chances of detecting a dark matter particle.
That's the idea.
And have these experiments found anything?
There have been a few tantalizing hints.
Really?
A few signals that could be from dark matter.
Wow.
But we need more data to confirm.
So everyone is on the edge of their seats waiting.
Pretty much.
If we could definitely detect a particle.
It would be huge.
Yeah.
A game changer for physics.
You mentioned these detectors are often located in mines or something.
Yeah, sometimes.
It's amazing what lengths scientists will go to.
It is.
Just to try to study this invisible universe.
It's a real testament to human curiosity and ingenuity.
Absolutely. Okay, so we've got these underground detectors, but you also mentioned particle accelerators.
Yeah.
So how do those fit into all of this?
It's a completely different approach.
Right.
Kind of the opposite of underground detectors.
Also.
With the detectors, we are passively waiting for a particle to come to us.
Okay, yeah.
But with accelerators, we're actively trying to create them ourselves.
Create dark matter.
Yeah,
Oh,
by
so-
smashing particles together at incredibly high speeds.
Like super fast.
Extremely high energies, yeah.
To try and recreate the conditions of the early universe.
Exactly, like a mini Big Bang in the lab.
Hoping that some dark matter pops out.
It's just,
And what kind of particle accelerators can do that?
the Large Hadron Collider, for example.
Oh, yeah, the LHC.
The one in Switzerland.
It's the biggest and most powerful one, right?
It is.
They smash atoms together at near light speed,
Pretty much, yeah.
hoping to create dark matter.
It's a long shot, but if it worked, we could study those particles directly.
It would be a breakthrough.
Yeah, it would be.
Okay, so we have these two main approaches to finding dark matter.
That's right.
Sensitive detectors looking for interactions underground, and powerful accelerators trying to create the particles directly.
Yeah.
Scientists are really pulling out all the stops.
We have to. It's a tough problem.
Let's say we do find out what dark matter is.
Yeah.
What could we learn? You mentioned it could revolutionize physics.
Oh, absolutely.
And lead to new technologies.
Right.
What kind of things are we talking about?
Well, first off, finding dark matter would complete our understanding of the fundamental building blocks of the universe.
What?
Our current best model of particle physics, the Standard Model, doesn't explain it.
So it would be a big change for physics.
A huge change. We'd have to extend the Standard Model or come up with a new one.
And that would open up whole new areas of research, I imagine.
It would. Maybe even whole new fields of physics.
So it's not just about satisfying our curiosity. There could be real-world applications, too.
Oh, for sure. Throughout history, discoveries in physics have often led to amazing technologies.
Yeah, like electricity and computers.
Exactly.
Well, what kind of technologies could dark matter lead to?
It's hard to say exactly, but maybe things like spacecraft propulsion.
Spaceships powered by dark matter.
Maybe.
Wow, that's incredible.
Or new forms of energy or communication technologies.
This is mind-blowing. Revolutionizing physics, spaceships, new energy sources. It's incredible.
It really is.
But there's also something bigger than that.
What do you mean?
Well, this whole quest to understand dark matter,
Yeah.
it's almost philosophical, isn't it?
I think so, yes. It's very humbling.
To realize we're surrounded by this vast, invisible universe.
And we're just starting to understand it.
It really makes you appreciate how much we don't know.
It does.
And inspires us to keep searching
Absolutely.
the fate of the universe.
Yeah.
Okay, so how does dark matter play into that?
Well, it all comes down to gravity. Dark matter's gravity is what holds galaxies and galaxy clusters together. But it also affects the universe's expansion.
Wait a minute. I thought the universe was constantly expanding. How can it be holding things together and expanding at the same time?
It's a bit of a tug of war.
Okay.
You see, the Big Bang started the universe expanding outward,
Yeah.
but gravity wants to pull everything back together. And dark matter, because it makes up so much of the universe's mass, it has a really strong gravitational pull.
So dark matter is kind of slowing down the expansion.
Like a cosmic break, yeah.
So the question is, how strong is that break?
Exactly.
Will it eventually stop the expansion and cause the universe to collapse?
It's possible.
Or will the expansion just keep going forever,
That's the big question.
leading to a cold, empty universe? What do scientists think is more likely?
It depends on a couple of things. How much dark matter is out there and how it's spread out.
Okay.
But right now, it looks like the expansion is actually accelerating.
Accelerating. Wait, so it's expanding faster and faster?
That's what the data suggests.
Wow.
And that's where another mystery comes in. Dark energy.
Dark energy. Hold on. You're losing me.
Yeah.
We're still trying to figure out dark matter, and now there's dark energy, too.
I know it's a lot, but dark energy is another invisible force
Okay.
that seems to be pushing everything apart.
So it's like anti-gravity.
Exactly. A repulsive force that counteracts gravity.
So dark matter pulls things together. Dark energy pushes them apart.
Yeah, it's a cosmic balancing act.
So what happens next? Does the universe expand forever or collapse?
It depends on which force is stronger. Dark matter or dark energy.
So dark matter isn't just shaping galaxies, it's also tied to the fate of the universe itself.
Absolutely.
That's incredible. We started with wondering why galaxies don't fly apart, and now we're talking about the end of the universe.
It's amazing how these things are connected.
It really is. So dark matter is key to understanding not just galaxies, but the entire universe.
And everything in it.
Well, this has been an incredible journey.
It has.
We've learned so much, but it feels like we've only scratched the surface.
There's always more to learn.
That's the beauty of science, right?
Absolutely.
Every answer leads to more questions.
And that's what keeps us going.
Well, I want to thank you for joining us on this deep dive into the mysteries of dark matter.
It's been my pleasure.
And if you're as fascinated by the universe as we are, be sure to subscribe to Cosmos in a Pod for more explorations of the cosmos. We'll see you next time.
See you then.